We will start here a series of lectures on fatigue design. As we know, fatigue is a very important aspect of mechanical design because most of the failures that are observed in real life are caused by fatigue. There are varying estimates, but many people believe that fatigue failures may account for as high as 70 to 80% of all failures of mechanical components. So it is kind of an important topic. So what I would like to do is cover a number of subcategories within fatigue design in the next few lectures, and we will try to address a variety of methodologies that will be used in specific applications. So as you can see here, I'm going to use the outline for the chapter that we wanted to talk a little bit about the introduction to fatigue in metals and describe qualitative aspects of fatigue failure and the approaches that we will use in fatigue design. And the approaches that we will use will basically be three different approaches that are shown here. One is called the fatigue life, based on the stress life method, and the second is based on the strain life method, and the third that you can see here is the linear elastic fracture mechanics methods. So we have three of them to assess the fatigue life. Then we would move on to talk about qualitative aspects of fatigue, such as endurance limit and the modifying factors that are used in practice, discuss the importance of stress concentrations, and then how to deal with fluctuating stresses, and how to classify the different levels of fluctuations. And then we will devote some time on fatigue under combined loading, because that's important if we have torsion and bending in shaft design, for example. And then finally, we will just look at surface fatigue strength as a qualitative aspect of fatigue. And in these lectures, I'm not going to address the stochastic aspects of fatigue design. So I will first explore with you, as an engineer, when you see a component, how can you determine that fatigue was involved in its failure? And let's just go through a few of these pictures that can show us different examples of real components that have undergone fatigue failure. So in here, what we have is an example that shows the different stages of fatigue failure. First, a crack is initiated at one location. So let's just kind of say that we have a surface location where the crack is initiated, and then that takes a very, very long time, the initiation, maybe millions of cycles sometimes, to initiate a small crack. Once the crack is initiated, then it can propagate fast in stage 2, and stage 2 it opens and closes. So as it opens and closes, then you see that you get what is called beach marks, and those are because of the openings and closings of the crack. And then as soon as the crack size reaches a certain level, so this whole area here is now cracked, the remaining part of the component, in this case is a shaft drive, is not sufficient to carry the load, and you get ultimate failure as a result of void formation and interlinkage. So this is kind of the traditional way that we understand qualitative fatigue failure. And let's see, as an engineer, how can you tell that there's fatigue failure? In these types of illustrations, we see three different kinds of components. One with no stress concentration, and the other one is with mild stress concentration, and the third if you have severe stress concentrations. The same is repeated on the right. This is under high normal stress, on the right under low normal stress. So what happens is that if you have no stress concentration, you get the initiation point on the surface. If you have a round cross section, and then you get these beach marks until you have failure. If you get stress concentrations, then the propagation is faster, as you can see here, and it proceeds much faster because you have higher levels of local stresses. The bottom is for cross sections that are not round, and then you can see that the initiation of the cracks start from the corner, usually from the corners where you have high stress concentration. For the case when you have low nominal stress, the failures are very interesting because it takes a very, very long time of successive layers of propagation before you get any failure. So you get similar pattern to high nominal stress until the remaining section is very, very small, because the applied stress is very small, and therefore the remaining section that carries the rest of the stress becomes small, that it would fail after a very long time because the applied stress is small. If you have stress concentrations, the same happens, but the propagation is much faster until you get failure in a very localized zone. If you look at other types of fracture processes so under different loading, then similar things would happen under unidirectional bending. So unidirectional bending is very similar to the case that we have looked at under axial tension. On the other hand, if you have reverse bending, then the cracks can initiate from both sides, as you can see here from these figures, and they interlink directly in the middle. So these are all observations that can help us decide if we have encountered a fatigue failure of a certain kind. Another observation is that if we have fatigue failure under what's called rotational bending, which is a small oscillation of the shaft to give it like a bending oscillation, and under torsion, where you have a torsional stress that oscillates, and in this case, in the torsional stress, then you can get these beach marks at either 45 degrees or at 90 degrees, depending on the ductility of the material. So this is ductile here, and this is brittle type behavior. And the telltale is that you get these beach marks that are propagating at an angle to the surface. So these are all examples that shows us, as you will see from in practice, there is a branch that's called forensic engineering. And forensic engineering, you build the expertise as an examiner, and you look at the component and you decide from your experience what happened to the component. So it's like a CSI of failure of components of, let's say, you have a problem or a catastrophic failure of a particular accident, and you want to piece it together and find out what is the culprit and what caused it. So these qualitative observations are useful in our understanding of general failure. Now let's look at a few examples that illustrate fatigue failure of real components, so we can appreciate visually what they look like when they fail. So here you get fatigue failure of a drive shaft, and the drive shaft has actually undergone fatigue, and you get some kind of an initiation of a crack at B due to the stress concentration in the keyway. And at C, you have the final failure at this location because the cross section has been reduced drastically from this point to this point. So this reduction is a result of the propagation of fatigue cracks in successive cycles. So it's very similar to what you would think that if you look at the trunk of a tree, and the trunk of a tree will just kind of from year to year will grow in circles or in a band structure because of the oscillation in the temperature and the growth that goes with the oscillation of the temperature. So it's been a similar phenomenon where with each cycle you get a little bit of growth, and then it accumulates over a very long time to cause the fatigue failure. So let's look at other examples here where we see a fatigue fracture example, and this is initiated again at a stress concentration zone due to the mismatched grease hole. And in this case, the fatigue crack initiation is right there, and then you can see as you have propagation of the crack, it just kind of moves around and fills in, so the crack is continuously growing until you get no additional space for the material to carry the rest of the load, and then you get eventual failure either by brittle or by ductile mode, depending on the type of material we have. This is another example of fatigue failure, and in this case we have a connecting rod. It's a forged connecting rod, and if you look at it, you see that you have a rough surface here, so it's not likely that a fatigue was initiated here, and you get a smooth surface in this zone here. So once we have a smooth surface, then we would think that maybe this is related to fatigue failure. And in fact, if you examine it very carefully, you can see that the beach mark started here, and then they skirted around the hole, and they started to propagate until they completely circumvented the hole, and then the remainder of the crankshaft is not sufficient to carry the load. So in this case, it initiated at the flash line of the forging at the left. So this is the flash line. This is a projection of the flash line right here. Next is an example of fatigue failure, which is kind of, I find interesting, because as you've seen most of the other failures in the previous examples, the crack is initiated always at the surface. Not only that, but at a discontinuity. So we would think, okay, if we're designers, we just have to go after these discontinuities and put fillets and round them and grind them and smooth the surface, and here we go, we avoid the fatigue failure. Well, this example that I show is very interesting because the fatigue failure in fact started from inside the material out. And how it is started, because when you do some casting, the homogeneity of the material becomes different. So you might have some parts of the material that are that have different grains, or they have triple point junctions or stress concentrations at what you see here at the flake, and that will start the fatigue crack that could be small inside the material, and it looks like this. So in here, the fatigue crack is started clearly started at this initiation point at the forging flake internal to the part, and then it grew, and it grows like circles in here. It seems like it doesn't know about the outside boundary until it comes very, very close to the outside boundary, and once it does, then you get the failure marks that are here because the material is ripping, and then you get voids and interlinkage until you get the eventual failure. So that's an interesting example of fatigue failure. Another example here is that you get a double flange trailer wheel But note here that stamp marks are points of stress concentrations, and in fact it turned out to be that these points have led to the initiation of cracks in the flange, and you get a fracture here and another fracture here as a result of these stamp marks of the components. Another example is a fatigue failure example is a landing gear torque arm assembly, and in this torque arm assembly you have a lug, and then the lug had a fracture at the connection with the torque arm. And in this case the design is such that if you inspect it closely, then you get a lubrication hole going through the structure, and this is a lubrication hole because you have to get oil to lubricate the connection with the landing gear. However, the fracture just have gone clear across, so the fracture, you get a fracture going across here. So it seems like with some modifications of the design that you get the loophole not from the at the thin section, but maybe at a wider section of the assembly, so you can avoid some elements of stress concentration. So from these examples that we've seen here, it appears that we have really to understand the fatigue at a qualitative fashion, we have to think about the origin of the initiation of the cracks, where they initiate and how they propagate. And generally speaking, we are dealing with either ductile materials or brittle materials. So the ultimate way that the crack is going to proceed is going to proceed by exceeding a certain limit. If it is ductile, for example, it can exceed the yield strength of the material, and the material starts to deform plastically in the remaining section, and then it will rip apart and lead to gross failure. If it is partially elastic or brittle, then the eventual failure will be based on exceeding a limit of fracture mechanics. As we've seen before, once we know the crack length and we know the fracture toughness of the material, then there will be only one type of stress that the material can take before that crack will propagate, once its stress intensity factor is greater than a fracture toughness. So in other words, to summarize, as we will see later, we will find that cracks propagate slowly, one by one. So we will find an equation that describes the rate of change of the crack size as a function of the number of cycles. And that's assuming that they have nucleated. So the nucleation phase is very difficult to determine, but assuming that inspection gave us a crack size that has been there for a very long time, but it just suddenly appeared, and we have inspected it and we determine its initial size, then we will follow the crack, and the crack will propagate until you reach a limit. And the limit is one of two things: either yield limit, plasticity driven yield limit, or a limit based on fracture mechanics, as we've learned before. So that's kind of what I described here is the linear elastic fracture mechanics approach to understanding lifetime of components. Generally, to deal with fatigue problems, we have three methods. The first method is the stress life method, which is good for low cycle applications. So low cycle applications is very and in this, like the low amplitude, so low cycle amplitude, and in this case this is easiest to implement, and we will call this SN method, as we'll see here. And then the second, so this is number one. Number two is the strain life method, And this is more difficult because I have to do analysis, cyclic plasticity at localized regions. So I have to look at every localized region and do cyclic plasticity, and then predict the lifetime based on the relationship between the strain amplitude and the number of cycles to failure. And then finally, the third method is more of the more modern method based on linear elastic fracture mechanics, LEFM. And linear elastic fracture mechanics assumes that we have a crack, and the crack grows until it reaches a critical value, and beyond that we cannot stop it anymore. So these are the three different methods that we have at our disposal. So here first we will just talk a little bit about how fatigue data is collected, since we're going to use some of this data later. So in this case, I will describe the stress life method, and the stress life method will use a sample, and the sample that is used is based on an idea developed by an engineer, and the engineer his name is Moore. So he has a machine that's called a Moore high-speed rotating beam machine, which is very common in testing for fatigue for samples that we have. And the idea is that the sample is subjected to pure bending with no transverse shear. So the dimensions are chosen, that the sample, the length is 3 7/16, and it is very highly polished, and you can have the surfaces of the sample are kind of hourglass surface. So we know that if we have failure, is going to be in the middle section, and the sample is rotated, so it is rotating like here, and while it's rotating, we have a load that we can load up the two sides with a load, let's say a load P here and a load P here, while it is supported on the end. So we have two supports and two loads. So it's looks like a beam, and the beam here is supported from the two ends, and is loaded down equally on these two sections of the specimen by weights. So as it's rotating, you'll see that, let's say that if it is static, then what happens is that the bending moment, if you draw the bending moment diagram, you get 0 here, then the bending moment will rise up to this point here, and then remains constant up to this point here, and then declines again. So what happens is that there is a region in the center where M is constant, and that's very important because we have a constant applied bending moment, and the constant applied bending moment will give us the load that is doesn't vary, doesn't have gradients over the middle section. So if you have initiation of a crack, the crack is not going to go from a low stress region to a high stress region, but it will propagate pretty much on the uniform applied load. So this is an important part of the design of this specimen shape. The other aspect is that as it rotates, you have a bending moment. So the bending moment, the top is going to be under compression, the bottom is going to be under tension. But if it rotates, then the bottom will become flip to tension, and the top will flip to compression. So you have each section or each element or fiber on the outside of this specimen is going to see a fluctuating stress from tension to compression of equal magnitude. So it's a very nice idea to develop this, and therefore you can get many fatigue cycles by changing the rotation speed of the machine and by changing the loads on the sides of the specimen, and therefore you can develop failure criteria based on the results of this test. So that's as far as the testing is concerned for stress life methods. And the results of this test are usually put in the form of a graph that shows you the stress amplitude that determines failure as a function of the number of cycles to failure. Note that this is a log scale to the base 10, and this is also a log scale to the base 10. So we have log graph, and each point here gives you a relationship between what we call S on this side and N on this side. That's why it's called the SN diagram. And note that S is that in reality, if I look at the stress as a function of time, as a result of this rotation of the Moore machine, you get tension, and then you're going to get compression cycle, and you continue on like this. The amplitude of the stress cycle, the amplitude is actually S. So S is the amplitude, and therefore we can have small amplitudes, or we can have very large amplitudes like this. Either way, we would get different results. So we have here very large number of cycles to failure for the small amplitude, and here we would have a low number of cycles to failure. And these are the coordinates. This is the coordinate, low cycles to failure, low cycles to failure. And then when you go to a very small amplitude in this region here, then you get a high number of cycles to failure. Well, it turned out to be that if you get to a very small amplitude like this, then the number of cycles to failure become infinite, become very, very large. So in this case, we have what is called the endurance limit, and the endurance limit is labeled here S endurance as a characteristic of the material. So we will discuss the endurance limit in a little bit more detail later on as a design parameter, but for now we understand that the results of the stress life test is that we get a relationship between the amplitude that causes failure and the number of cycles at which failure would occur. So you have a variety of amplitudes and a variety of number of cycles to failure. And if you look at the graph, you have three different, you have two main regimes. One is called the low cycle regime, which is right here. And that is for any number of cycles approximately below 1,000. We would call this fatigue low cycle fatigue. And for any number of cycles approximately above 1,000, we will call this high cycle fatigue, including the range that goes into infinite life. So to summarize, we have two main areas, or two main levels of behavior. One is the low cycle fatigue, and the other one is high cycle fatigue, and the delineation between them is approximately 1,000 cycles, approximately, so give or take. And in the high cycle fatigue, the ductility is what matters, and in the low cycle fatigue, the strength is what matters. So if you have a material that has a lot of ductility, then it will do well in the low cycle fatigue. However, if you have a material that has high strength, it will do well on the high cycle fatigue. And with that, I think we're going to conclude this lecture, and we will continue in the next lecture looking for other applications.